Good afternoon, students. Today we are going to see about classical mechanics. Yes, so far we have seen about the mathematical physics. We have seen about vectors, Stokes theorem, Gauss theorem, Bernoulli's theorem, Euler's theorem, Laplace equation, Poisson's equation. And later we have seen about the coordinates, orthogonal curvilinear coordinates, spherical polar coordinates, cylindrical coordinates. Now we are going to see about the classical mechanics. Yes. So classical mechanics, the main important is the Lagrangian mechanics. What about it deals with? Classical mechanics is have a two divisions. That is one is called Newtonian approach, another one is called Lagrangian and Hamiltonian approach. Before earlier we have followed only the Newtonian approach, that is force F is equal to ma, that we have to given as dp by dt, that is change in the momentum with respect to the time. And later we have followed the Lagrangian and Hamiltonian approach. Yes, which with the help of a D'Alembert principle, we are using the virtual work. So it is given with the coordinate t, comma v, where time and the velocity. L is equal to t minus v, h is equal to t plus v. Oh, what is h? H is nothing but Hamiltonian. L is Lagrangian equation. So how we can get this differential equation of the system? Yes, we are going to, if we apply for the system, this Lagrangian and Hamiltonian, how it behaves, that we can see. If it apply for a system, the Lagrangian mechanics will have a coordinates as x, y and z axis. So these are the transformational equations. Already we have seen in the second unit the spherical polar coordinates, curvilinear coordinates and cylindrical coordinates. So from this it is easy to understand you that Lagrangian mechanics will have an x is equal to r sin theta cos phi, y is equal to r sin theta sin phi and z equal to r cos theta. These are the transformation equations. Yes, so each particle here needs three coordinates to specify the configuration of the system constraint. Yes, we have if now have n particles, then we have three n coordinates, where m is the equations of constraints and n is the number of degrees of freedom. Then we can write n is equal to 3 minus m. Yes. What about the general coordinates? The same, what we have seen about n minus, n is equal to 3n minus m. That is the given here in the designated these coordinates by the symbols q1, q2, q3 up to qn. So these are called generalized coordinates for this transformation of equations. Now we can see what is the n. We are saying n. What is meant by that? That is nothing but the degrees of freedom. Yes, the number of coordinates required to specify the position of a system of one or more particle is called the number of degrees of freedom of the system. Thus, if the system is a single particle, then the Cartesian coordinates are given as x is equal to x of q. If it is a 2 degrees of freedom, we can write it in x and y axis. And if we have a 3 degrees of freedom, we will write in the x, y and z axis. So if it is in 3 coordinates, then the motion will be in space. So what is my constraints? Yes, the limitations on the motion. We are saying that is have a three coordinates have a motion in the space. If it is in free space or in particular sphere or particular cube, we can say. So the limitations on the motion are often called as constraints. Constraints are divided into two types. One is holonomic constraints, another one is non-holonomic constraints. What is by holonomic constraints? All the constraints of the system can be expressed as equation in the form of phi of q1, q2, q3 up to qn, and their equivalent is called holonomic. Otherwise, if we cannot able to write in this constraints, that is in this coordinates, then it is called as a non-holonomic constraints. Yes. See, we can write it in the form of phi q1, q2, qn with q1 dot, that is with its differential equations. Then it is called as an non-holonomic equations. And we can write this example as a spherical polar coordinates and equations. The generalized forces. Next we can say about the Newton's law cannot be derived, but Lagrangian can be derived from the generalized forces. Yes, it is given as a particle undergoes a displacement delta r. If a force is F, then it is given by the virtual work delta W is equal to F dot delta R. The equation is given here. So these are the generalized equations for generalized forces for the general equation for the generalized forces. So for conservative systems, with respect to the kinetic energy of the system, we can define all these equations, and we can discuss indirectly in the board. These are some examples. Simple harmonic oscillator. We know that F is equal to kx into 1 minus 2x. mx square. So with the non-conservative force and with the velocity independent, we can derive the equation, Lagrangian equation for this simple harmonic oscillator. Then single particle in a central field. All those things can be derived from the Lagrangian equation. Thank you, students.